Okay, in this video we're going to discuss procedural animation. So this is a very broad topic and there are many strategies. There are some very simple approximate strategies and there are more complex strategies. So let's go in order, starting with the simple ones. Okay, so hopefully you can see a little lizard walking around on the screen. And basically, the way this works is for each of the little legs, there is a effector point, and the segments of the legs, these guys, they are there are two degrees of freedom. So there's the angle theta, and basically you have to optimize the angle theta such that the two segments, when you forward simulate them, they land on the end effector. And there's a very simple approximate way to do this, so let's discuss that first. Okay, so I have a little drawing pad here. Okay, so basically you're going to have 3 points. So this is going to be your arm, right? Let's say this point here, the red one, is the end effector. And basically you have, for each of these points, you have a distance. So let's say this is D1, and this one is going to be D2. And you're going to have segments that connect these points. So to forward simulate, basically you would draw, let's say, this first point first, and then you would draw the second point in a random position. Let's say here. But then you calculate the distance from the parent node to this new node, and if it's greater than or less than D1, basically if they're not equal to D1, then you would normalize. So you would divide this vector by its so let's say we call this V1. So this is going to be your first approximation, V1, and you would do V1 times equals D1 divided by the magnitude of V1. So it's going to be a vector that points in the same direction as V1, but it's going to have this magnitude. So that's how you normalize V1. And to do the second point, you would just add another V2 here. Let's say this is called V2. And you would do the same thing, but with this point as the parent. So let's say this is your V2. And then once again you would have V2 times equal D2 divided by the magnitude of V2. And that's how you forward simulate this point. Okay, so the problem is that when you forward simulate this, these points, you're not guaranteed to land on the red point. And that's what we want to achieve. So a very simple strategy is to move this point to the red point, right? So let's say you take this end point and you move it here, and then you would do the backward simulation. So you would do the same thing, but instead of picking random points, you would pick where the point already is. And now you would do, this is going to be your V2. Okay, V2. And you would once again normalize it like we did before. V2 is going to be equal to D2 divided by the magnitude of V2. And so this is going to move this point a little bit closer. Maybe right here. And then you would do the same in this direction. Note that we know the original location of the parent node, of this root node. So let's say this is our shoulder location. So let's say this is going to be called the shoulder. And let's say this is going to be and the red one is going to be the target end effector. And so you would do the same with this point, with this last point, but given this as the parent. So let's say you put it here. And notice it doesn't exactly align with the shoulder. So this is going to be V1. And we, once again, multiply V1 by D1 divided by the magnitude of V1. So no, as I said, this backward simulated point is not necessarily going to align with the shoulder exactly. But what you would do then is you would just repeat. So you would move this point to the green shoulder point and then do the same thing. And then you repeat this a few times, maybe 3 or 4 times. And you're pretty much, well, it depends on the complexity of your arm or leg, I guess. But you're pretty much guaranteed to have a good good fit. Of course, there's an issue where the red point is too far away, right? So let's say you have right here is your shoulder, and let's say your target end effector is way over here. But in that case, you would just you would be reaching for the end effector. You're not guaranteed to reach it, but it would just be reaching towards it, which is fine. Another issue is self-collisions. Let's say you have, well, that's a little bit too involved. We're going to just discuss that a little bit later. But this is a simple strategy you can use to do inverse kinematics. Notice there are no additional constraints, so we'll get into that later. For example, a constraint might be you don't want to self-intersect, or you don't want to have specific angles. So let's say you don't want to oh, that's a good example. Let's say you have an elbow, right? So let's say this is your elbow, and you know that your angle should be in this range, right? So this is going to be your theta. And if you go this way, then that means that you basically broke your elbow, right? And that's a constraint. So an angle like this would be a bad angle, right? So this would be bad theta. So okay, so this is a special type of problem. It's called constraint optimization problem. So I gave you a very simple strategy, but let's get into a slightly more complex strategy where basically you have a energy function. So let's say you have theta 1 and theta 2, etc., theta n. So these are your degrees of freedom. Let me put it, degrees of freedom. And let's say you have an energy function. So E as a function of all these thetas is going to be some energy function that you define. For example, it could be the distance from the simulated end effector to the target end effector. So let's say this could be the distance. You can use distance squared. So distance squared from forward simulated end effector to the target end effector. And the reason we want to use a distance squared is because, well, okay, you can use L1 norms, but they're a little bit harder to optimize. Of course, this is not going to be easy to optimize in either way, because you have you're going to have a lot of cosines and sines, and another issue is that these angles, they wrap around, right? So they are in the range from, let's say, theta 1 is going to be in the range from 0 to pi, but it's going to wrap around, right? Or 2 pi or something like that. So just because 0 and 2 pi are far away in the coordinate space doesn't mean that they're actually far away, right? Because it wraps around, which means that 0 and 2 pi are actually the same number. Okay. So if you have an energy function such as this, then what you can do in order to deal with these constraints is to have soft constraints, right? So let's say you might have a say here you might have a penalty for bad theta plus penalty for self-intersection. Of course, by self-intersection I mean if you have a more complex arm, let's say you have 3 segments, let's say like this, and then maybe like this, right? So there's a self-intersection, and we don't want that. So if that's the case, then you would have some differentiable function, such as a exponential function that would blow up whenever you have a bad theta or a self-intersection, but that would be 0 in other cases. And the reason we want to have a easily differentiable function is if you want to calculate the analytical derivative for this thing, then that's much easier to optimize, right? Because then you can just use gradient descent, or you can use Newton's method or something else, and you would always know the analytical derivative that you need to follow. Another strategy that you could use would be constraint optimization. So let me maybe start over here. Let's say constraint optimization. And basically here we're talking about Lagrange multipliers. And Lagrange multipliers is a very neat idea. Let's say you have a this is your constraint, right? And let's say you have some function in the background, and let's say here is your optimum, right? So this is some global, or not global, but some local optimum. And this is going to be a small value for E, and everywhere else is going to be a large value. So that means that if you want to find a point along the constraint, so on this circle, which is the smallest energy, which has the small energy value, right? Let's say here. Then you know that the gradient and the normal of the constraint are going to be parallel, right? So let's say this is your gradient, and let's say this is going to be your normal. And Lagrange multipliers basically tells you that the normal is going to be equal to lambda times the gradient. And what you would do is you would solve for lambda, and that would give you a system of equations in terms of x, y, and z, or theta 1, theta 2, whatever. And once you solve that system of equations, that would give you the set of thetas that satisfies this this set of constraints. Of course, you might not get a minimum or maximum, right? So there might be saddle points as well. So let's say you have, or you also might have other candidates. So let's say this one here, but then this one here also satisfies this equation, right? But it's not necessarily going to be the smallest optimum. So you would have to check these and then just pick the smallest optimum. So of course that only gets you onto this constraint surface. Once you get there, then you would have to use some other optimization method to get to the local optimum that you're looking for. But hopefully if your function is sufficiently simple, you're going to have so you might have different regions. Let's say you have over here a bad region, right? So this might be a self-intersection region. Self-intersection here. And then let's say over here you might have another bad region, which would be bad thetas here. Or you can have other constraints. So these are not necessarily the only types of So these penalties are not necessarily the only constraints you can have. So let's say you want to have a physically realistic animation, right? So you could add another constraint here, which would be the physical realism. Let's say you can have the center of mass has to be under the so let's say you have 3 or 4 legs, right? So under the 3 legs that are on the ground, right? So maybe you want to move 1 leg at a time, but you also always want to use, or always want to keep the center of mass under the 3 legs that are on the ground. And if that's not the case, then you could have another region here that that you would try not to fall into, right? And what this helps you here is if you have a constraint optimization. So let's say this constraint would be just the theta 1 equals the limit theta, right? So let's say theta 1 is in the range from 0 to 30 degrees, right? So you can say this here is theta 1 equals 30 degrees, right? Then equals 30 degrees. Then that means that eliminates one of the self-intersection issues that you're going to, or sorry, 30 degrees, like I said. You might have other issues, of course, but you're just going to have to check the optima that you get. Okay, so that's one approach. There is another approach which is a little bit more involved. So let's say you have a very, very hard problem, right? Let's say you have some sort of let's start over here. Let's say you have a bottle, right? You have a bottle here, and you have a narrow opening, right? And inside the bottle, there is some food or something, right? And then let's say you have a tentacle, right? So let's say this is your tentacle, and the tentacle is like, it has lots and lots of segments, right? And your goal is to reach this food using this tentacle, but without intersecting with the glass, right? So the tentacle is going to have to go inside the opening here and reach the food. In that case, all this stuff is probably not going to work, right? Because this is a very hard problem. So in this case, you're going to probably have to do a random search. Okay, so let's say you have this energy landscape, right? So let's say this is your bad region here, where you're intersecting the bottle, and then you have another bad region, and then you have this very narrow bottleneck, right? And then over here, you might have a region where the tentacle is actually touching the food, which is what you want, right? But you start over here. So you start at some point over here. This is your initial set of thetas, right? And it's not so easy to find this. I mean, it looks easy in this drawing, but it's not so easy because it's a multi-dimensional problem, right? And you're going to have, let's say, 20 different segments here. So this is going to be a 20-dimensional problem. So what you would do is you would start at your initial configuration, and then you would randomly sample the 20-dimensional sample space around this configuration, and you would check, are these points valid, right? That is, do these points hit the the bottle, or do they self-intersect, or are there bad thetas, or whatever. Are there some physical constraints that you introduced? Whatever, right? And essentially, if that's the case, then that means this point is in the bad region, and it's eliminated, right? The good points you can use as seeds for future samplings, right? And you could have some sort of a heuristic where, let's say, you calculate the distance from, let's say you calculate the distance from one of these configurations to the target, right? And that could be your heuristic. So let's say you would sample, but such that the distance is always decreasing. That might not always work, so you might have to give some leeway, right? So you might have to allow the search to increase this distance for a little bit, right? But basically what you would do then, let's say you have all these points, and at some point you're gonna have a set of points where there is a path, right? So let's say these are your edges, and you would have to check that the edges also don't hit these bad regions, right? So you would have to maybe have a small step size, and you would have to move in a linear direction. And if they do hit the bad region, you would have to move around it. But that's a much simpler problem, right? Or hopefully that's a simpler problem. But okay, so once you have a set of edges, so maybe the edges also go over here. Whatever can be connected is connected, right? Then you could use a shortest path algorithm such as Dijkstra's algorithm, or you can use A star, or whatever. There's a lot of algorithms for calculating the shortest path, right? And that would hopefully allow your tentacle to reach the food, right? So this is a more powerful method, but the issue there is that even if you do find a path that leads to the target, it might not be optimal in this sense, right? So there still might be some room for improvement. So once you do find a viable solution, you would still have to maybe do something like this here. Maybe use gradient descent. Let me write these down so you can use gradient descent, or you can use constrained optimization, or you can use Newton's method, etc. Yeah, so basically that's it. This is a good introduction to inverse kinematics. So this is what this is called. And of course, these types of tips and tricks, they're useful in many other problems. So, gradient descent is also used in machine learning, you name it. There's a lot of, or also the shortest path algorithms are very, very useful. So this is a very good introduction to computer science problems in general.